Hey, Jen, we can't hear you on Zoom.
Hello.
Okay, now
All
we can.
right. For those of you who have not yet met me, I'm Jennifer Seavey, and I'm the director here at Shoals Marine Lab. And for those of you, well, I should say to all of you in the room, there's also people online. So we are doing this in two ways. We're also recording it, and it will end up on our website. And these happen all summer long. And so when you leave this island, you can join us via these talks every Tuesday. So you are always welcome to join us here and look at all of the talks previous to that. So for those of you who don't know, Shoals is the largest and the oldest undergraduate focused marine lab in the country. It is run jointly by UNH. Thank you, Wildcats, and Cornell. All right, go Big Red. We are located here on Appledore Island in the Isles of Shoals. And every summer we bring these marine science talks to you on Tuesday nights. And our format is about 45 minutes of lecture and then 15 minutes of Q&A. So think up your questions. Don't be shy. We have plenty of time for them. If you are online and you want to ask a question, please use the Q&A box and I will read it out loud to our speaker and to everyone in the room. If you have any trouble online, Casey is monitoring the webinar and she can answer your questions. So just put in the chat if you're having trouble. And tonight, I am very happy to welcome Fadel Adib. He is an associate professor from MIT and he is the founding director of Signal Kinetics, a research group at MIT. His group invents new wireless and sensor technologies to interconnect, sense, and perceive the physical world in novel ways. And they apply this work across a big variety, broad arenas, but one of them is in the ocean. And he does all kinds of fascinating things at their lab, solving our challenges as marine scientists. And we want to understand the world. And he has spent the last 24 hours going across this whole island, learning about what we do. And I think he's going to talk to us a little bit about how his work can be applied to things like what we do. And a very important thing that we should applaud, he caught his first fish today here at Shoals Marine Lab. Very proud to have a part in that. And without further ado, here's Fadel.
Thank you very much, Jennifer, for the introduction. Hello, everyone. Thank you for being here. You know, I can't imagine a more awesome way to be spending my July 4th. Fun fact, this is my second July 4th as an American citizen. I'm originally from Lebanon, which is a country on the Eastern Mediterranean. And I moved here about 12 years ago for graduate school, and I have been here since. And spending the last 24 hours on this island has been a reminder of why this is an amazing country. It's because it's a place where great people and great institutions come together to do something that is nothing short of magical in reality. You know, as a scientist, you look around this island and you're so amazed by how it's basically self-sustaining. There's exciting research and courses going on. It's attracted passionate faculty and staff and leadership, as well as very ambitious students like yourself who come here and think about towards and work towards a shared mission. So it's my absolute pleasure to be here with you today and share with you what we've been working on that is relevant to what's been going on over here, and specifically about how we can bring the Internet of Things to the underwater world. Most of the talk is going to be focused on that, and depending on how much time I have towards the end of the talk, I'm going to be telling you about how we apply the same fundamental technologies to solve a wide variety of problems, even beyond. Now, before I start, I just want to understand a little bit of the audience, so I need a bit of help from you. First, I want to show of hands who here is a high school student. Okay, great. Who is an undergrad? Great. And what is that? Okay, no, there's also there. And who is faculty, staff, and support and leadership here. Wonderful. Everyone else? Nobody. Okay. Great. It always helps me to understand the audience. So I'm going to be telling you about how we can bring the Internet of Things to the underwater world, but I want to make this talk interactive. So I'm going to be asking you questions. I want you to ask me questions. Feel free to interrupt. All of the stuff that I'm going to be talking about is new. In fact, it's even new to me. So there's no stupid question. First, when I say Internet of Things or IoT, I might be using these terms interchangeably. What comes to your mind? Maybe someone can raise their hand and say, what comes to their mind when you hear Internet of Things? IoT, yes. Bluetooth, great, yes. Bluetooth is IoT. What else? Yeah. So localization, or like knowing where things are, that is part of the Internet of Things. Yeah. Yeah, please. Arduinos, why? Yeah, so that's great. All of these are good answers. There's a lot more. What else? Yes. Smart home devices. That's great. Yeah. AI is incorporated in IoT. That is also correct. Yeah. What is it? So what is that? Yeah. So everything that everybody said is part of the Internet of Things. Anyone wearing smartwatches? No. Yeah. Internet, that's IoT. Smartphone, it has Bluetooth, it has Wi-Fi, it has GPS, it has LTE. All of these are part of IoT. Anything that is connected forms the Internet of Things. It's things that are connected. Okay. And so today almost there isn't an aspect of our lives that is not connected to the Internet. From, of course, our smartphones and our smartwatches to our smart homes, connected cars, and so on. But there is something in this world that is not really as connected to the Internet as the rest of the world. And what is that? It's the ocean. Actually, very, very difficult to bring the type of connectivity. I mean, if you look around this room, there's more than 100, maybe 200 Internet IoT connected devices. You look at the same area in the ocean, and you'd be very lucky if there is one. Okay. So what I've been the past 24 hours, I spent some time going around, and what I wanna do is I wanna show you some of the photos that I collected, and I wanna ask you, if you could bring connectivity to these areas, what would you use it for? Like, for example, I use my Fitbit or my smartwatch to monitor my health, or to connect, or to send data. So these are some, can anyone, like, what do you see here? So you see a solar panel. This is on a USV, on a surface vehicle that is deployed. What else? Seals, okay, and? Yeah, so there's also Kelly, who's tracking the CTV from Rove. How would you want to use IoT in each of these? So actually, does anyone knows what this the surface vehicle is? Maybe the people who are actually working on it can would like to share. Great, thank you very much. So how can IoT, similar to smartwatch, if I can bring connectivity and sensing in these areas, how can it help? Yeah. That is absolutely right. You can deploy it and get measurements. Why is that? Do you know why that's difficult today? Why it's difficult? Why don't they just like leave it there? Very good answer, or maybe someone else. Yeah. The battery. Why is that a problem? Yeah, it's going to run out of a battery. So that's one of the problems. The other thing is it's actually expensive. And so you deploy them, it's the cost of deploying them. The other thing is that it was also being inserted and then moved up. So we're trying to sample the water column. So if you want to get the same type of measurements from it, you need a much larger number. So you multiply this battery problem by the number of sensors that you need to deploy. So great, so that's for the CTT. What about the seals, for example? How would you want to use IoT for that? Yeah. So being able to track them, and especially being able to track them underwater, that's where it becomes extremely difficult to track them. Yeah. Being able to identify them at an individual level, identify and track. Also, I think Roger was telling us that there's these fingers that are underwater that are used for like monitoring the sharks. You could also use sort of IoT sensors there as a way for monitoring the environment and not having to replace them every 6 months. What about in the surface vehicle that is trying to monitor the harmful algae blooms? How would you want to use IoT here? Yeah. So that is the first thing that you want to do. What's interesting is actually this already sort of has a backhaul, but so it has a wireless antenna. But what you could do is that instead of having just one that has this huge, relatively huge solar panel, you can have 100 of them. And if you have 100 and all of them are connected to each other, now you can get much richer data, and you can use that data to better predict and understand harmful algae blooms and protect against all of the environmental hazards. Okay. So all of these are reasons why we want to bring the Internet of Things to the underwater world. But actually, when I started working in this space, almost right when I started as a professor at MIT, what motivated me was another question, which was, what plays the biggest role in the world's climate? And I wanted to do something that can contribute to what I perceive to be the biggest problem that we are facing. And as I looked more into this problem, I realized that by far it is the ocean. It impacts and it determines our weather. It mediates our entire climate system. And it is also the part of our world that has been most impacted by climate change. Over the past 2 decades, the ocean has absorbed more than 90% of the excess heat content that we have emitted into the atmosphere. The ocean today also holds more than 93% of CO2 that is in the planet. Now, with the oceans playing such a huge role in the world's climate system and being impacted by climate change, I started wondering, well, how much of the ocean have we measured? Or if I ask this question in a different way, what percentage of the entire ocean has never been observed? What do you think? Most. 80%, 99, probably it's closer to 99, but it's definitely more than 95%. I don't know the exact number. Actually, we don't even know, but it is more than 95%. It could be 97, it could be 99, but we have not observed most of the ocean. And this is a problem because it means that we also do not understand that in what ways, for example, climate change has impacted over 95% of our ocean. And it also means that our climate models are still missing very important data that is critical to understanding some of the most complex processes. And as a scientist and an engineer, I started thinking about, okay, how can we observe all of these hidden parts of the ocean? And I come from the IoT and wireless networking background. And the idea that I had is that we wanted to build an Internet of Things to observe the underwater world. We wanted to take sensors, deploy them at scale, measure CTD, capture images, measure sound, and have them collect this data and send it back to us. And as my group and I started to do that, we faced a problem, which you alluded to, which is the battery life of underwater sensors is extremely limited. And when we look deeper into it, we realize that one of the biggest challenges is that when you have a sensor, it wants to transmit its data. But to do that, it relies on these underwater transmitters that consume something of the order of a few watts. And it's not easy to replace them. So if I were to deploy a CTD in the ocean and I want to replace its battery, every time I need to send a research vessel. And if it's in the middle of the ocean, I have to pay like $50,000 a day to replace its battery and come back. And this is why most state-of-the-art sensors that are used for continuous monitoring, the vast majority of them, if you want to get data all the time, can only last for a few hours or days, after which their batteries stop. And it got us thinking about ways that we can reduce the power consumption of underwater communication, because if you can reduce the power consumption, then we can make these wireless sensors last for a very long time. And to do that, we invented a technology that enables underwater backscatter networking. So I'll explain to you what this technology is. The main thing about it is that it enables sensors to communicate underwater without requiring any batteries. So the way I want to explain this to you is by comparing it to how traditional communication works in underwater environment. And if you're not familiar with that, no problem, I'll give a 5 minutes. So in many of these environments, if you look at a lot of the sort of state-of-the-art approaches, you, for example, have an underwater drone or a surface vehicle, or it could be even a ship or a submarine or something that is near the shore that wants to ideally communicate with a large number of sensors. So let's say a temperature sensor. Now, the sensor wants to transmit data. And unlike over the surface, it cannot use Wi-Fi or Bluetooth. Why? Because Wi-Fi or Bluetooth rely on wireless signals, which are in the radio frequency, so RF, and these die exponentially fast in water. So instead, what if it wants to send its data, what it needs to use is sound. So it has a speaker. The underwater drone has a hydrophone or an underwater microphone, and it encodes its messages using sound, and it transmits them. The problem with this approach is that generating sound is what consumes a lot of power and drains the sensor's battery. So our idea was that we go ahead and we put the speaker and the microphone both on the drone. And our sensor instead simply has an acoustic reflector, which you can think of as a mirror. Now, when the drone sends data, sends an acoustic signal, the signal is going to reflect off this reflector and come back. So if my sensor wants to communicate data, all it needs to do is to switch its reflector between two reflective states. So for example, it says, oh, I want to reflect, or I want to absorb the energy. And by simply switching between two states, it can communicate in bits of 0 and 1. And once you can encode something in bits of 0 and 1, then you can generate any message that you want in binary. And so by simply turning a switch on and off, we're able to encode any data, for example, this temperature data, and communicate it to the remote receiver. So in comparison to the traditional approach, where the sensor generates its own sound and that drains its battery, in our approach, the sensor communicates by reflecting an existing sound that is underwater. Now, you might be wondering, what did we do? We just shifted all the power consumption from the sensor to the drone. And the answer is yes, but that's exactly what we wanted to do. Because now this can be on a drone or it can be the shore, and it's transmitting this, it has its own power source. And you can deploy a very large number of sensors, each of which is extremely low power, and use that mechanism to communicate their data. Now, of course, all of this is great, but there was still one question, which is how can we control the reflections of sound? How can we control acoustic reflections? And so for that, what we did is we used piezoelectricity to design programmable acoustic materials. For those of you who are not familiar, the piezoelectric effect was discovered in the late 1800s by the Curie brothers. And what it is that it is the ability of certain materials to transform mechanical energy into electrical energy. So For example, if you take a piezoelectric material and you try to measure the voltage across its terminals, and let us say that you have a speaker and the speaker transmits sound. Now, as we know, sound travels as a pressure wave. So when it hits the material, this material vibrates, and then you start having an electrical signal across its terminals. So it transforms mechanical energy, which is sound, into an electrical signal, which is the voltage. And this is how piezoelectric materials behave. But remember, what we want to do is we want to use them as reflectors. So to do that, all we did is we added a switch across the terminals of the material. When the switch is open, the material behaves exactly like before and translates sound into electrical signal. What's interesting is what happens when the switch is closed. When the switch is closed, it means that the two terminals are connected to each other. It's like a short circuit. And when you have a short circuit, you cannot have any voltage. So you have an incoming signal, you cannot have a voltage. This material cannot vibrate. So there is energy that is coming in. Where does this energy go if this material cannot vibrate? It has to be reflected back. And so by simply attaching a switch and turning this switch on and off, we're able to translate this material from an absorber to a reflector. And we call this technology piezoacoustic backscatter because it uses the piezoelectric effect to backscatter or reflect back sound or acoustic signals. What we've shown is that this kind of communication technology consumes 1 million times lower power than state-of-the-art modems, and then lower power than this underwater communication technology that has been in use for the past half century. Not only that, what we also showed is that our sensor can also harvest energy in the absorptive or non-reflective state. And it can run entirely based on this harvested energy. And that allows us to make this entire sensor system battery. So let me show you a video of one of the experiments that we ran, one of the earliest experiments that we ran on MIT's campus. This is done in a large experimental pool. At the far end of the pool, there's a projector, which is a speaker, and the hydrophone receiver. And here's our sensor. It's connected to a circuit, and the circuit has a light emitting diode. Now remember, the circuit has no battery, but as I play the video, you'll see that the LED lights up because it is able to harvest enough energy from sound in order for it to power up its electronics. And it is also able to communicate data back. So what I'm gonna do is I'm gonna take the hydrophone that was at the far end, and what I wanna show you is how we're able to sense these changes in reflection. So I'm gonna show you a plot. Over here on the y-axis, you see amplitude, and I want to plot it as a function of. This here is the signal that we get. At around 2.5 seconds, the speaker starts transmitting sound. So you see a jump in the amplitude that is received. And at around 3 seconds, the node starts backscattering. So which means that it starts switching between two states. And the hydrophone is able to detect these small changes between these two states. And because it can detect them, it can record. And building on this basic idea, we've developed different algorithms and techniques that allow us to deal with other reflectors in the environment and scale to many different ones. This is one of the first prototypes that we built. Over here, we fabricated and 3D printed our transducer. One of the questions that I often get is, how do you know in which direction you need to reflect the signal back? And the answer to that is, when I talked about a reflector, it's really an analogy. In reality, you can actually reflect in all directions. So you can make it omnidirectional. And we also build the hardware for energy harvesting, bidirectional communication, and integrated different kinds of. One of the other things that is important about this technology is that this whole thing ends up being very low cost. And for folks who work in the with oceanographic equipment, these usually things cost thousands or tens of thousands of dollars. This whole thing costs $100. And it consumes less than 20 miles. And over the past few years, we've been building on this in different ways. For example, we've been developing different node designs that make them even more efficient. We've been developing the communication theory and different protocols. We've also shown that you could use them for underwater localization, similar to how Wi-Fi and Bluetooth don't work underwater. GPS also does not work underwater, and you need to instead rely on these very power-hungry systems that run out of batteries. So we showed that you could use our sensors for localization so that you can either, for example, tag an animal and then track it as it moves around, or use them as anchors for robotic navigation. Recently, we've also been working on bringing AI to underwater sensors, as well as building imaging systems using our technology. Now, I don't have time to go into all of these. So instead, what I want to do is I want to choose a couple of them and show you some of the demonstrations that we've enabled. So we were very excited after we showed that you could do communication underwater, and we showed that you could also measure temperature and pressure using our sensors. And we became more ambitious. And for about 2 years, we worked on building the world's first battery-free and wireless underwater camera. So we announced this paper, this project last year, and actually I think this is what caught Jennifer's attention. So I want to show you a video of our setup. So over here to the right, you can see our measurement setup. You can see there's a camera, there's a flash, and I'll explain it in a bit. And we're trying to image an underwater coral. And to the left, you see the received and reconstructed. As I play the video, you'll notice 3 things. First, the camera is emitting a flash because in deep sea environments, you might not have light. So you want to have illumination. Second, the flash is in different colors. And the reason is because we realized that the lowest power image sensors are monochromatic. So they only see grayscale or black and white. And so we invented this mechanism that you can emit different colors and then combine them to reconstruct color images. And the third thing is it was reconstructed in chunks because of the limitations of different constraints on the memory and the computation and the bandwidth of underwater environment. All of this was run based on the harvested energy, even the LED, even the flash. All of this is based on the sound that it is able to harvest. So here are some of the other photos that we captured. This is of an African starfish. This here is of pollution in the wild. So actually my students took our camera and they went out to one of the lakes in New Hampshire and they imaged a plastic bottle. And this over here, it's a pretty remarkable result. What we did is we took the seeds of a plant, we planted it in an underwater environment, and we just watched it sprout over the day. And the reason this result is remarkable goes back to how I started by saying that today, it's difficult to do long-term observations because you're worried about your sensor running out of battery. Well, here's a camera that is entirely batteryless, that can run on harvested energy, and so you could use it for continuous monitoring over a long period of time. Another thing that I also wanted to talk about is some of the work that we've been recently doing in underwater AI. So we said, okay, you can show communication, sensing, imaging, localization. Can you also bring AI and machine learning underwater? And the reason is because there's many applications. Like, for example, these sensors are very compute constraints because you're running on very low power. But can I run a whole AI model? And can I use it to recognize the sounds of different species? And we collaborated with some researchers at Imperial College, and we showed that even our earliest models can achieve 85% accuracy in classifying different species based on their sounds. And what is very exciting is in the machine learning space, if you show 85% at the first result, it means that it's actually, you could easily get to 99% in a couple of years. And while we've been working on this for a few years, of course, we're very excited about the ability to be able to sense the ocean at scale using these projects. There's so many open problems, and there's so many things that we could still work on. And as researchers, we love these challenges. So we, for example, brought down the power consumption to from a few watts to a few microwatts, so about 1 million times. Some of the stuff that we're working on now is sub-microwatts, so another 100 times. If we were to build our ICs or integrated chips, which we can also do, then we can bring them down to nanowatts. And if you bring it down to nanowatts, then you can, there's a lot of important applications because then even if you have a small battery, this battery can probably last 100 years now. There's also many interesting theoretical problems. How do you scale these? We've shown this, for example, with dozens of nodes. How do you scale them to hundreds or thousands of deployed sensors in the environment? We're now working on how do you use this for backscatter imaging. So this is actually a pretty interesting concept. You usually use sonar for mapping the sea, or for mapping either seafloor or doing imaging. The problem with sonar is that the further you get away from it, the worse the resolution becomes. Think as if you have a beam, and the further you are away from it, this beam becomes wider and wider, so your resolution becomes worse. One of the things that we're working on now is if you were to deploy a small number of our sensors, for example, out there on the coast, near the shore, then you can start using them to multiply the resolution of your sonar, even if you're further away. And this has many applications. I mean, there's many defense applications, but there's also many marine tracking applications. You can start using them. If you want to have, for example, shark monitoring, you want to know where it is, you throw a few of these around, and you can use this deployed network of sensors to be able to track them, even without putting these sensors on the sharks themselves. There's also exciting applications in robotic navigation, like you let a robot roam the sea, and how does it find its way back? Well, if it has our sensors, it could like drop them as breadcrumbs, and it can make its way back to its source once it's done with it. And there's also many other exciting areas, from more advanced imaging to imaging and AI to long-term deployments. Another area that we've been working on is also like, how do you build the world's first batteryless micro robot that can just roam the ocean? And this is another area and another project that we're excited about. So we've probably run more than 10,000 experiments. Here you can see two of my students, Audrey and Jose. This is with one of our first sensor nodes that has temperature, that can collect temperature and pressure measurements. And all of this started with us, with our desire to build an Internet of Things to observe the underwater world, because there's, it roots back to these climate applications. There's so many other applications. So you could use them to discover rare species or track rare species in the ocean. So maybe the marine biologists can help me here. Out of every 10 organisms, I mean, there was a study, I think in the early 2000s, that out of every 10 organisms, a certain number has not been discovered yet. Any guesses, or anyone actually knows? It's 9. 9 out of, scientists believe there was a study in the early 2000s that 9 out of 10 marine organisms have not been discovered. Since most of life is in the ocean, it means that we have not discovered most of organisms on our planet. Yeah. That's a great question. And I actually looked into that. I was like, how do they code this? And so what they actually did is, there's this stuff from like sampling theory. So they went into, for example, a new area that they hadn't explored. And then they got a sample of it, and they started looking, how many of these have we like seen or not seen before? And then they realized that they have not discovered most of them. But this is it's probably 9 plus or minus some bound of error. And I like this question because I looked into it when it first came up. Thank you for asking that. So there's many applications, from discovering new species to being able to monitor existing species and understanding more about their migration pattern. Another big area is aquaculture. Some of you might not know, it's the world's fastest food growing sector. 1 in 3 people rely on the ocean as their primary source of protein. The United Nations and the World Bank have, the World Food and Agriculture Organization have both said that if you want to feed the world's population over the next 3 decades, we need to get aquaculture right. But it's actually very difficult to monitor aquaculture farms because it's difficult to deploy sensors. If you want to monitor them, for example, and prevent harmful algae blooms from destroying a whole season, you somehow need sensors that are deployed there that can monitor these hazards and enable responding to them. And that's another area where underwater IoT can help. So it goes back to one of the things that I actually saw earlier today, and how we can potentially help with new IoT sensing technology. And there's many other applications: defense, disaster response, robotics, and so on. Another area that I find to be very exciting is in extraterrestrial exploration. So some of you know that NASA scientists discovered subsurface oceans in Saturn's moon Enceladus and Jupiter's moon Europa. As you can imagine over there, once you send the sensor, it's even more difficult to go and replace its battery. So we're working with them to incorporate our technology as part of their future space missions so that they can search for life in extraterrestrial objects. So there's so many exciting applications. There's many exciting technical problems, and that's why I personally get very excited about this. One of the things that we've done is that we've released a lot of the code and schematics and tutorials. As I started by saying that all of this is new, it's also new to us, but it also builds on many different fields of research. So we end up collaborating with researchers from all sorts of backgrounds so that we can make a new technology a reality and so that we can see how we can translate it. So I promise that if I have some time, I will tell you about some of the other things that we're doing in my lab. Most of the talk up until now has been focused on, can we build an Internet of Things to observe the underwater world? But we also ask other questions like, can we bring the Internet of Things inside the human body so that we can monitor the body from the inside and protect against diseases or respond to new health hazards? We also asked, can we see through walls with Wi-Fi? And actually, this was my first project, major project as a graduate student at MIT. And the basic idea was that I wanted to take a Wi-Fi device that is like my phone, point it at a wall, and see people behind the wall, how they are moving without any sensors on their bodies. And then can we take this a step further, and can we make augmented reality headsets like Apple announced the Vision Pro? Can we make these things that give us X-ray vision? You folks are who's familiar with what's X-ray vision? Yeah, Superman's ability to see through walls, exactly. So can we give that to humans? So I don't have time to go over all of these, but I want to just tell you about a couple, one of which actually is it was my first project as a graduate student at MIT, and which is, can we see through walls with Wi-Fi? And then I'm going to jump to one of our latest projects. So here, what we did is we put a wireless device in another room behind the wall. In the bottom left corner, you see the output screen of the device. And notice the red dot because it tells you where the device thinks the person is at every point in time. Now, before I play the video, I want to say that the spiral on the ground is only there to show you the level of accuracy. As I play the video, you'll see that the red dot tracks the person very accurately, even though no device on his body, entirely using this Wi-Fi device that is on the other side of the room. This person is me when I was a graduate student. Because you can sense people, you can not just get their locations, you can also monitor their, like for example, you can track their hand movement. For example, over here, he's pointing at different appliances. And because we can track his arm movement, we allow him to like turn off the TV by just pointing at it. And of course, because the device works through walls, even if you leave a room and forget to turn off the light, all you need to do is to point in the direction of that. And all of this done using a device that is on the other side of the wall in the adjacent room, and it's monitoring people using their Wi-Fi, using the wireless. We worked on it quite a bit. Actually, this project started back in 2013. And over the years, we've shown like a lot of things. We showed that you could use existing wireless device, Wi-Fi and 5G, to get people's locations and gestures. We also show that you can get people's breathing, heartbeats, emotions, stress levels, all using wireless signals reflected off of their body. We started a company out of my PhD thesis that is currently using the technology to monitor patients with Alzheimer's, Parkinson's, COVID-19. And it's actually now the main use is in accelerating drug discovery. So the reason is all of these diseases are associated with changes in either vital signs or mobility. So for example, when COVID-19 broke out, we used our devices to be able to We place them in nursing homes so that we can monitor elderly patients and the progression of, for example, their breathing without having to have the nurses go in and be exposed and themselves contract COVID. Today, it is used for discovering new drugs faster, because what we do is we take our devices and deploy them in like thousands of homes. And we use them as a way to see how people are reacting to the drugs rather than having them wait to go to a doctor and only them monitoring them. Actually, this ended up becoming a whole industry. The next generation of Wi-Fi is going to have the technology that we built. It's also in 6G. Google, Samsung, Amazon, all of them built products on the market that use our technology. There was a question. Yeah. You're absolutely right. And so the question is, what are the ethics that are related to this, especially in regard to privacy? And it's something that we actually thought a lot about. One of the things is when you're working on a fundamentally new technology, it's very exciting, but always extremely scary. And I can give examples maybe after we run out of time. There are two ways of dealing with this. A is you build the countermeasure, whereby you can actually today prevent someone from using this against you if you don't want them to use it. And we've built things that technologically enable that. The other thing is we've actually engaged a lot with policymakers, because it almost feels like, there's a lot of time where the government is almost playing catch up with technology. So we went and we engaged with policymakers so that we put the policies in place before these things hit the market, and so that people are protected against them and nobody can use them in nefarious way. Yeah. Not yet, but thank you for asking. Sure. Actually, speaking of engaging with policymakers, it's also one of the reasons why a few years ago we were invited to the White House and we demoed this to President Obama. There's multiple funny stories from that White House visit. At the time, I was still a PhD student, and I was the subject of the demo. So we were monitoring me and monitoring my falling and then my breathing and heart rate. The video of this demo is actually available online. If you go and check it out, you'll see that my friend Zach, at some point in the middle of the video, he puts his hand on his mouth and he starts laughing. And the reason he starts laughing is because the device was monitoring my heart rate, and my heart rate was 110 as I was demoing. Actually, I realized the next video, it has sound. I don't know if it's gonna play, but I'll try. Should I know? Okay. It doesn't matter. I'll say it. So I usually like playing it. So 10 years later, now we're bringing augmented reality to X-ray vision, to X-ray vision to augmented reality. So actually, this is one of our newest projects. We announced it this year. What we're doing is we are using the existing headsets and allowing people, for example, to find items that are inside closed boxes. So for example, she's looking for a shirt that she cannot find. And the way we did that is we built this antenna that fits on the HoloLens. And it's conformal, it's flexible. And what it does, it also relies on RFID stickers. I don't know if you're familiar with them, probably most of you are wearing them. So there are these like batteryless tags that are embedded into many of our clothes. And they cost about $3. So let's say that she clicks on the menu, she selects what she's looking for. And this headset then uses wireless signals, similar to how I was describing it before. It powers up these tags. These tags then, there are tags inside the boxes. You cannot see them, but they're inside. And then they reply back. And using this, we're able to create a virtual 3D world that maps the real world environment. And so as she moves around, you see we're able to track her headset. And this sort of green-yellow sphere indicates where the headset thinks the item is. And so as she moves around, it becomes more and more confident. And then it tells her, okay, this is where the item is. And once she knows where the item is, she goes ahead and it picks it up. Here you can see that it picks it up. And then even when it picks it up, you can verify, oh, yeah, you picked up the right object. And this has different applications. For example, in winter housing, it could be used to find items that are missing. It can help with a lot of logistics, which is why your item does not arrive in mail. They start being able to use our items, our technology. It can also be used in retail stores to help find items. And it also has some other applications, for example, in manufacturing, where you want to label the environment and try to interact with it. That you cannot otherwise. Pretty exciting, augmented reality with X-ray vision. And actually, we recently started another company that is commercializing the technology, which is why pretty much the only time that I could come here was on July 4th, because all of the other time I've been spending either at the startup or in my lab at MIT. Of course, none of this would have been possible without my amazing group who you see over here. I have my postdoc Ahmed, who's been visiting with me. And he's worked, for example, on a lot of the underwater backscatter stuff. One of the things that he's shown is that when we started, I showed it to you in a small experimental pool. One of the things that he demonstrated is that we can actually communicate over hundreds of meters, and that theoretically this can be extended to kilometers or potentially tens of kilometers. Okay, with this I'll wrap up. So I told you about how our mission to bring the Internet of Things to the underwater world, and I'm happy to take any questions. Thank you.
I just want to see a raise of hands if your mind was just blown. Okay. Just check in if I was alone.
Hi. Thank you for an amazing talk. Have you considered the environmental impacts, especially of the underwater application? For example, have you envisioned if the animals would mistakenly swallow those tools?
Yeah, I mean, this is a very good question. And there's actually two types of potential environmental problems. One of them is will the animals swallow these food? And for that, there's multiple solutions. There are advanced ways of sort of probably designing them where you avoid them being swallowed. But the other way is you could also design a lot of these from biodegradable materials or from biocompatible materials, so that even if they were to swallow them, there's biodegradable circuits and biodegradable piezoelectric material that could be used for similar things, such that if they were to swallow them, they would excrete them after a while. But the other part is sound. Like, I mean, we're transmitting sound, and what are the levels of sound that are going to be emitting, and are these going to be harmful to the animals? And one of the really nice things about what we're doing is we're able to transmit sound at much lower power. The other thing that we could do is we could leverage the existing sound that is underwater and backscatter that sound. Like one of the projects that I'd like to work on is using the existing whale songs, for example, and backscattering those and eliminating the need to transmit the sound signal altogether underwater. So very important questions, and we'll figure them out as we start moving closer towards deployment, but we already have hints on in which direction to go. Yeah.
So you were talking with when you visited the White House, how you were able to monitor your heart rate. Is that something like a Fitbit for animals, where the tracking devices is that? Oh, can you talk more about that, I guess?
Yeah. So the question is, can you use that to monitor animals? And the answer is yes. We've actually used it to monitor, for example, one of the interesting things is in many of these, some of them happen almost like chance. So my advisor, she had a dog, and the dog was in her lap, and we were getting 2 breathing rates, and it turns out that we were monitoring the dog's breathing rate as well. So you can, and some people are using our technologies for monitoring in experiments. There are also ways, one of my students had an idea of how you use our underwater technology to monitor vital signs of marine animals, again, in a non-invasive way. So there are some very interesting connections.
Regarding privacy, I was wondering what your opinions were on using this technology for military purposes, such as like finding a fugitive.
Yeah, so there are, of course, many defense applications for these technologies where they could be used in hostage situations to understand what is going on. And some of the work, I believe, has been transitioned in that direction. We decided, for a number of reasons, we decided to focus on the healthcare applications. And that's where we ended up putting a lot of effort and advancing the technology. But of course, there's also applications in finding people like under rubble in an earthquake. So I don't know. To be honest, at this stage, I lost track because so many people have built on our technology. There's thousands of people that are building on it. And you keep seeing it in the news, which is great for me, but we're not actually, what's interesting is that we're not working as much on this area anymore because there's so many people working on it. And part of our mission is to, similar to what we're currently doing underwater, is to envision what is possible, make it possible, create the tools for others to build on it. And then once these tools are amplified and out, then we move on and see where we can bring in most impact and benefit.
I was wondering, because you showed us images that you were able to take on your camera. I was wondering how long it took to render those images, and if you were continuing to like update them, and if you ever took pictures of like very fast, like moving animals, like fish or something like that.
Yeah. So the question is, how much time does it take to get these? The photo that I showed you, I think it was 2 hours. But late last year, my group brought it down to, I don't know if you remember, what was it, 1 second? 10 seconds. Yeah, 10 seconds. And you could use it for like very quickly. You could do it for fast animals, but then it still takes time to transmit that image, which is why then we started building these AI models that can summarize this data and only send the images that you need to send and store them. I have a certain philosophy when it comes to research, which is first show that it is possible. And when you show that something is possible, then you have enough smart people to make it efficient and fast and protect its privacy, make it biodegradable. This is why sort of our mission is to create new technologies that enable us to connect and sense the world in ways that were not possible.
For your like energy harvesting technology you were talking about in ocean sensors, can that work from like any sound, or does it have to be like the excess sound from the drone?
The question is, can it use any sound? Originally, this is what I didn't talk about as much in the node design. Originally, it was like a specific kind of sound. Then we expanded it such that it's a broad range of sound. There's always going to be some range that you can potentially harvest from. But if you go outside that range, it becomes less efficient. So you need to wait for a longer time before you can potentially harvest. So it really depends. I'll have to give you a more specific answer of how much time it needs. I would have to look at the exact answer. But the technology itself is general in the sense that you could use it for any type of solution.
Okay, so I have 2 questions. One, what was the time scale of this? So like, how long did it take you to get to this point? Kind of like a little bit about your journey. And then 2, what's stopping this from becoming like globally viable, and like what's stopping it from being used in personal use and hitting like the global market?
Follow up about what are you asking? Because there's in my experience, it takes about basically I had my first startup that was based on my PhD research, and then the second one that I'm working on now. We just started with the third one that is for ocean. And it usually takes about 5 years from when you have the original idea to when it starts becoming something that is relatively mature to be able to push it out. It takes us actually a relatively small amount of time. Like the very first idea took us maybe 4 to 6 months to demonstrate that it is possible. And then we kept building on top of that a lot, because when you discover something, then there's so many ways in which you can grow it. And then my whole team has been working on expanding it. And then you start trying to understand what are the problems that you can solve, and what are the first problems that you can absolutely solve. So we're now almost, it's been about 4 years, almost, or 5 years. This year we started thinking about commercializing it and starting a company. And one question sometimes I get is, why do you start companies as opposed to you like let someone else figure it out? And the reason is, in my experience and speaking to a lot of my faculty colleagues, if you invent a new technology and you want to translate it to practice, you have to be the one pushing it. Otherwise, it's going to take 30 years, 20 to 30 years for it to be pushed out if you're going to rely on someone else to do that. And so my colleagues who are like close to retirement, they admire the work that my group does, because they're like, you guys managed to push this stuff out in a short time. It ends up being much more like very difficult, because it's a different set of skills that doing research than entrepreneurship. But it is important. You have to be in the driver's seat, because then people look at you, and if you believe in it, then, and you're putting your effort in it to make it a reality, then you also understand the technology. And so then it takes about 2 years from when you start transitioning it to real world deployment. And probably, I'd say maybe 5 years after that to be in the mass market. And I give this example based on my first experience with like the seeing through walls. Now we're going through the second experience with sort of this AR headset type stuff. And actually just a few months ago, like Ahmed was co-leading one of the ventures from our lab that is taking our underwater sensing technology and again, starting a new company.
So you said that this is like essentially a renewable energy source, and I just wanted to ask, how far do you think you could push this? Like, would it only work on small electronics, or is there eventually a point where it can be a biofuel?
In general, so the question is could it be a viable renewable energy source in the ocean? When it comes to questions like this, I prefer to think about the problem than about sort of the extent in which you can push it. Because if I were to tell you that we're gonna build a wireless battery-free underwater wireless camera using our technology, if I were to tell myself this 3 years ago, using this renewable energy source, the answer would have been no. But how could we do it? What we did is we went ahead and we thought about what does a camera consist of? Can we rethink the entirety of how you build a camera, and now build a camera that is very low power that runs based on this technology? And so we rebuild this whole stack. Can we get AI models and run them on this? And then we're like, okay, you're not going to get the AI models that run in the cloud on data centers and need many GPUs, and you can adapt them to them. I don't know to what extent we can still push the technology, but I think we also, like, it's going to be very difficult for us to figure out. And I think what personally excites me is if someone comes and says, oh, I don't think you can do this. And then we're like, no, we'll do that if it's sufficiently interesting. And we will, working with my team, we probably do. And that's what people told us when we first started working on the seeing through walls. Actually, people did not believe us that it works until we got them and made them try it for themselves. And this is what people told us in the beginning when we started working on the underwater research. So we get motivated by things that people think are not possible. So I cannot really tell you what is not possible, because I don't believe that there is something like that technologically. Thank you.
Thank you so much. Okay, so as I said, all these talks are recorded and they are online. You can show your friends back home all of this. You can see past Rock Talks and future ones. And when you're off the island, you can join us live and ask questions live. And next week is Anna Silverio, and she is a marine biology graduate student at UNH. And she is working on long-term independent and fisheries independent and fisheries dependent fisheries catch data from the state of Texas. And she's modeling how extreme events like hurricanes and freezes and global pandemics affect coastal sport fish populations in Texas. So that's coming up next week. All of this, of course, is on shoalsmarinelaboratory.org, and you can find out everything there. Thank you again for an excellent talk.